Okay, so we're looking at pure modes. Pure mode solutions of the Schrödinger equation. Various Schrödinger equations. And by that I mean different potentials. Okay, so the first one we did was a free particle. Is equal to 0 everywhere. And the solutions we got. Remember the pure mode solutions can be factored into a spatial part and then a very specific time dependent part, oscillatory time dependent. Okay, so these were the plane waves. So the spatial part is just the complex exponential. For k is greater than 0, they're right traveling. K less than 0, they're left traveling. And we have the specific relationship between omega and k, dispersion relation. Have that relationship. Otherwise, there are no restrictions. So omega can be anything, any positive value. So omega is greater than 0. And then we have two possible values of k for given omega. No restrictions. So the energy spectrum is continuous. So 0 is a possibility. And the energy is h bar omega. Calculate the probability. Complex absolute squared of that, which gives us what? What's the complex absolute squared? In other words, you're looking for the square of the amplitude. The magnitude 1. Kind of a weird answer. It is a kind of a funny answer because we're allowing the electron to be everywhere. There's no bound on where the electron can be. Probability is the same everywhere, but then if it's an infinite extent, we don't have a total probability of 1. So there's a problem with trying to normalize. It's called normalize. That is, find a coefficient, a factor out front here, such that if we integrate this over x, we get 1. So there's a problem with normalizing this function. I'm not going to worry about that. The important result here is that the probability is the same everywhere. And so this 1 is kind of funny, but we would use n squared here. Point is that it's uniform. There's no, with a plane wave, the probability for where the electron is found is uniform, no preference for one place or another. And it also doesn't change in time. Okay. So that in the probability, there's no hint of motion. We'll come out later, as we investigate this, we'll find a way to calculate occurrence. So this is like saying that the water may be flowing this way, but the height is remaining uniform. It's the same everywhere. It doesn't tell you whether the water is flowing or not. Just that the height is the same everywhere. Okay, so this doesn't mean that there's no motion occurring. It just means that probability is the same everywhere. Okay, so that was one, the free particle. Then the other one we did last time was the particle in the box. Can I erase this? Everybody okay? Particle in a box. PIV. Particle in a box. So V of x is equal to 0. Let me write it this way. It's piecewise continuous. So for X outside of the box, it's infinite potential, which means it pushes the electron away. The electron cannot get into that region. But there's a 0 potential in between inside the box. So it's like a free particle inside the box, except that we have the condition that the wave function and at both ends. Yes, yeah. Who's first?
Are one of those supposed to be negative infinity?
No. The potential is positive infinity. So draw it like this. And then push this up to infinity. So there's no way for the electron to get out of the box. The field just becomes infinitely large, infinitely hot, so it can't get out. Was that your question? Yes.
I don't know if you said this yet or the last class, but is a particle in a box is like that a rough example of like a electron field?
Yeah, so you could confine, you can do this even in microelectronics. You can confine an electron to, by having an electrostatic field that it can't, that's very hot. So this is a kind of idealization, infinitely high, that you can't do. But you make it arbitrarily hot, which you can do to make it, you could make it higher and higher. So you're confining the electron to some region. And what we'll find, when we look at the expression for the energy, that the energy of the ground state depends on the size of the box. And if we're talking about a box on the order for an electron, on the order of angstroms, that the ground state energy is on the order of electron volts. And so that's a typical thing for microelectronics. Okay, so we found that again, we're looking for pure modes. We have a particular time dependence, and everybody moves at the same frequency, and there's only one frequency for a pure mode. And so we found the pure modes look like this. I'll explain all the factors here. Let's see, I n x over L. Okay, so those are the pure modes. Those are the spatial parts of the pure modes. That satisfies the Schrodinger equation with b equals to 0 and matches the boundary condition. The wave function vanishes on each end of the region, and then the wave function would be 0 outside of the box. Okay, that's the thing I should also specify. This is for this region, and psi of x is equal to 0 for x outside the box. Okay. The energy associated with this mode, with each of these modes. So n is an integer, a positive integer, goes up without bound, because the electron can never have high enough energy to get out of the box. It's always confined. It has an infinite potential well, confining it. So the energy spectrum is square integer multiple of the ground state. So unlike what we had for a piano wire, the frequency was an integer multiple of the base frequency, the integer of the frequency of higher modes. For a particle in a box, now for an electron in a box, the base Schrodinger's equation has a different relationship between the frequency and among the frequencies. So n is called the quantum number. It labels these states. I want to talk about the nature of these states. Here's one thing to notice. So if I add back in the time dependence. And the frequency, by the way, omega n is also n squared times the base frequency. So I should go ahead and put that in here, n squared times omega 1t. Okay, so that's now a solution to the time-dependent Schrodinger equation, but it's a pure mode. It's not the only solution to the time-dependent Schrodinger equation, but it is a special kind of solution, which is pure mode. Yeah. Rob.
What does that say inside the sign? Is that pi nx?
That's this. Okay, so for n equals 1, the wave function looks like this. For n equals 2, the wave function looks like this. The spatial wave function for n equals 3, spatial wave function looks like this. Looks like a guitar string. It's exactly the same as the guitar string. The mathematical function is the same as the guitar string for the spatial part. But the frequencies are different. The spectrum of frequencies is different than you would get on a guitar string. Okay, so now let's, hang on just a second. Let's square this. Okay, the time dependence drops out when you take the complex conjugate, multiply it by itself. You just get 1 for the time dependence, so it's the probability density in one of these pure modes is not changing in time. So pure modes are also known as stationary states. They're called stationary states because the probability is independent of time. And that's because they have a very simple time dependence here. And when you multiply this by its complex conjugate, you get to 1, so it doesn't depend on time. Okay, so let's plot the probability for these modes, not the wave function, but the probability. So we got to square that. Okay, so these are the wave functions. Psi1, Psi2, 3. Now let's look at P1, P2. The probability is positive. And so we take the square of the sign. And so it looks like this. All right, the sign starts off with a slope of 1. The square of that is parabolic. The square of the linear function x is parabolic. P2 then looks like this. P3. Okay, so notice that where the wave function crosses 0, the probability has 0. But the probability is parabolic there because the wave function is linear. Where it crosses the axis, you square that, it's parabolic. And so the probability has zeros, but they're not cusps. Yes, sir.
Is the probability function, is that like what we're ultimately trying to do with solving the Schrodinger, so we can like?
It more than that, yeah. The energy spectrum, probability is something that should be measurable. And other things, we're going to get some other things from the wave function as well, which has to do with the speed of the particles. So we're extracting out information. This wave function has for us information about what the electron is doing. But it's statistical. You should always think about this in terms of an ensemble.
Yeah, so it's going back to that whole ensemble idea.
Exactly right. So if I can prepare the particle in the ground state, and then I come back and look at where each one is, I'm only when I measure the position, I only get one definite answer. But I have to give 1 million people the same experiment prepared in the same way, ask each one to measure the location of the electron. It will be a particular value in here. Everybody has a definite value. But there is this statistical distribution among all of the people who have participated in the experiment. And then I could say there's an average, and there's a width. And that width is called the uncertainty. There's nothing uncertain for each person who's done the experiment. I have one particular value. It was right here. And you had one over here. And a whole bunch of people have some around here. Nobody gets it on the end. And nobody sees an electron there. Or at a place like this. But there is a statistical standard deviation for the ensemble. Right? It's a very important point. There's nothing indefinite about your measurement of where the electron is. It's just going to be different than anybody else, than other people, some other people, most other people will get some other value. Make a histogram of those results. The average will be L over 2. And the standard deviation will be some fraction of L. Width. Yeah.
What's L?
That's the width of the box. How narrow is the region that you confine the electron?
And this is true for this is generically true for any particle that is follows that way what we can predict behave using that equation.
Schrodinger equation? Yeah. This is a solution to the Schrodinger equation. The Schrodinger equation applies to any massive particle. We're treating it as a point-like particle, so that's one thing to consider. Right? There's a mass. That's the only thing that's the only characteristic that comes into this, the mass. Okay. So we could calculate then, so we want some certain things to be satisfied here. We want the total probability to integrate to 1. Well, the wave function is 0 outside the box. So the probability is 0 outside the box. Nobody's going to find it outside the box. So in this particular case, I can, the integral is only over 0 to L, and the probability is this, 2 over L sine squared pi n x over L dx. And that square root of 2 over L was chosen to make this integral equal to 1. Why that square root of 2 over L is there. So the total probability of finding it somewhere in the box is 1. We don't lose anybody from the ensemble. Okay, now you can also calculate, again, the probability is 0, and so in general, the average of x by weighting the probability by x, weighting the x by the probability, maybe is a better way to say it. And for the particle in the box, probability is 0 outside, so this is x times that. So there's an integral to do. And again, little n is an positive n. And it turns out for all values of little n, what do you think the average comes out to be? Right in the middle, L over 2, right? So this turns out to be L over 2. That integral gives you L squared over 4. So that you get the average value of x is L over 2. Okay, now notice, if I put it in this state, nobody's in the middle. So even though the average comes out to be in the middle, maybe nobody's there. It might be nobody's average. That means there's just as many above as below. right? This is made to the left, is to the right. But the average is not representative of any individual. The ensemble measure. Right, don't forget that. Okay, then the average of x squared, from which we can calculate standard deviation. Okay, now this does depend on n. And this is the homework problem to work this out. So, which one of these do you think has a higher standard deviation, a higher width? Third, right? This is broader. And this. So you should see this. This is increasing, and take the square root of this, right? The standard deviation, or the uncertainty in x, is called delta x. Take this. This should be increasing, but it should be less than L. This width has got to be less than L. So it's something less than L, but it's going to keep increasing as n increases. So there's going to be approaching an upper limit. Yeah.
So another way of saying, standard deviation is that capital delta.
Yeah, this is called the uncertainty. And
That's not a sub x, that's like,
now it's delta x. No sub.
that's not the function either.
It's not a function. The symbol is delta x. Defined as the uncertainty in x. So what is meant by the uncertainty in x? Remember, each person who measured the position of the electron in his box got one value, one particular value. There's nothing uncertain about that. The uncertainty is a measure over the ensemble of the distribution of different answers. We could go through here and take everybody's weight, and we could get a probability distribution for the weight. We need a bigger ensemble to make this meaningful. But we have some distribution. We might have more. We might have a gap in the middle, right? It's possible that we've got some in the middle near the average is actually not many people. So we get some kind of distribution. There's no uncertainty about your weight. What do we mean by the uncertainty? Is the standard deviation of the ensemble over, in other words, it's meaningful only to talk about it as a group. Okay? Yes, sir.
So is the uncertainty added because like you can't measure enough data points, I guess,
No.
to create like a normal distribution?
No, it's not a normal distribution. This is what it is. And it has nothing to do with small ensemble. This would correspond to a large ensemble. And it's going to look like this when you get to a large ensemble. It's all, if you don't have a sufficiently large ensemble and you're collecting measurements on a small ensemble, you're going to make a histogram out of that. It's going to be something not resembling this so much. As you increase the size of the ensemble, it's going to converge to this.
Right, and that's what I was going on, because I remember like back then statistics, it would be like conditions like 10% of the normal population.
Yeah.
And like there's so many electrons.
This is not a normal distribution.
Okay.
It's not Gaussian. It's this. It's not a Gaussian.
Just the probability.
Yeah, it's a probability distribution, but it's not a Gaussian. We will talk about Gaussian distribution. That's coming, but not there yet.
So uncertainty, so this uncertainty equation is the same thing as the standard deviation.
Yes,
And so why don't we call it uncertainty again?
that's just a name that's very common.
Oh man, that's not.
It doesn't mean that people are uncertain about their weight, or that when I measure the position of the electron that I'm uncertain about where it was. That's not what it means, and this is just creating a lot of confusion. It's an unfortunate word in that sense. It merely has to do with the statistical uncertainty inside of the ensemble, that there's some distribution of answers that people get. You collect all the measurements, everybody's got a definite result. There's nothing uncertain about individual results. There's a width to the distribution for the ensemble.
There's like a funny way of like comparing how that, at that point, how that relates to the average in some way.
Say that again, I'm not sure I understand.
Is a way of saying, I still don't understand what
The
it's.
width has to do, is related to the average in some way. The width around the average. So it's got to do with that.
That's not real, so, like, we solve.
It is the uncertainty. So when you're trying to make a normal distribution out of this, I think everybody's trying to fit this into a normal distribution because you want to have a value at which you cross here or something, you say 60% is this high. That's not what this is. Remember, that's only for a particular distribution, which is the Gaussian. This is the width. That's it. That's the definition of the width. It is.
So that is the actual width.
Yeah. But if you're wanting to try to draw a place where it intersects the curve, it doesn't intersect the curve in any particular place. And it's not true that 67% of the population is inside of the average plus or minus this.
Oh, is that the standard deviation? Is that what it means, that the standard deviation of the Gaussian? It's 67.
Just a Gaussian.
Exactly.
That's true only for a Gaussian. It's not a Gaussian.
So, okay.
Yeah.
So in order to get the right hand side of the uncertainty, you would have to use those P's
Yes.
in the interval.
Yes, sir. Okay. Exactly. Here's x, average of x. Here's average of x squared.
Yep.
This is delta of x. The definition of delta of x. It's not. There's no Gaussian distribution here. There's no. I mean, you could talk about sigma, but it's not a Gaussian distribution.
Right.
You could use the symbol sigma, and some people will, but it's not a Gaussian. And that's the danger of writing it as sigma, is you're thinking that there's a Gaussian associated with it. There's no Gaussian. Okay. So these are stationary states again. The probability doesn't change in time. The average is not changing in time. The width of the ensemble doesn't change in time. So in other words, if I hand out the samples prepared for everybody to measure, I say, wait 1 minute, then make your measurement of position. And then everybody comes back one of these three, for example, for the histogram. Okay, now I do it again, I say, wait 2 minutes. Trying to get the same answer. The probability is not depending on the time since preparation. That's why it's also called a stationary state. So pure modes, stationary states, the probability is not changing in time. Okay, so let's look at this ground state. This is really weird. What does this thing mean? So there is a lowest energy. Look how the energy, that ground state energy, means there's no mode lower than this. And so look at how this energy scales. The lighter the particle, the higher this energy. More massive this particle, the lower the energy. Also, the size of the box. If I increase the box, the energy goes down. You expect, under classical conditions, to be able to put the particle at rest and have zero energy. That's not happening for the electron in a box. I can't go below this value. There's no way to get it down there. So remember, in electromagnetism, you can take a charged particle like an electron and accelerate it, radiate. It'll lose energy. So this electron is free in between, but it hits off the walls. Every time it hits, it should be losing energy. Okay, so what does this mean? Something has to keep the electron energized. Something has to keep giving it energy, because it is radiating. guiding wave. There's two parts to the guiding wave. I have this book front cover. Okay, so these, can you read for us?
Oh, yes, sir.
Read that, the guiding wave structure.
The guiding wave structure associated with every particle consists of various powers of the phenomena, including zero-point field that guide the particle in various ways. The effect of the structure, along with that of the associated particle, is described statistically by quantum mechanics, in particular by the wave function, which is a solution of the Schrödinger equation. Quantum mechanics considers an ensemble of similarly prepared systems described by psi.
Maybe. All I want there, let's see, the 0-point field. So it talks about the 0-point field. Read about the 0-point. What is that?
The zero-point field, ZPF, is also called the vacuum state of the E&M field, which is a stochastic E&M radiation predicted by quantum field theory QFT that has a spectral energy density given by rho omega.
Okay, you don't need to read it. There are two parts, there are two characteristic parts of the guiding wave structure. The first is a resonating or interfering part, which is steady. When the particle, the system gets into one of these pure modes, it's a resonant mode. And this quantization condition is reflecting that resonating, interfering condition. Somehow the guiding wave structure is resonating inside of this box. The details of this we don't know. But logically, it's a very sound conclusion. The second part of the guiding wave is called stochastic. What do I mean by stochastic? Ready for the term? Again?
Stoic means non-changing.
Yeah, not stoic. Stochastic.
Doesn't that mean like there's like some so-called randomness?
Yeah, there's a randomness. Okay, so the randomness has to do with there's some kind of the guiding wave structure has both a resonating, but there's also a stochastic part. Some kind of random part, just like the Brownian motion. Remember the Brownian motion, the particle was bouncing around. It wasn't that there wasn't any cause for it. There certainly was a cause for the Brownian particles to be bouncing around. But the cause was hidden from us. The details of the cause are hidden from us. So it appears to be random. So random is an apparent thing, which is simply that we don't know about the cause. Doesn't mean it's intrinsically acausal without any kind of cause. This means that it's suppressed beyond our ability to detect. So we have the stochastic part keeps the electron from going below this level. Keeps pumping it up, it keeps radiating. And that keeps going on constantly. So when it's in one of these modes, these two things are combined in such a way that the particle remains in a kind of steady state, jumping around because of the stochastic, and it's also confined to the walls, and it's got this it's got this resonating structure. All of this is going on. Statistically, the result is captured by this wave function in terms of the ensemble. Yes.
So the stochastic nature, is that like leading into like how like the electron exists in like probability fields, like outside the atom? Like I remember from the chemistry, it would be like something and it'd be like
I know
little flower petal looking things.
That's this.
That's that. Okay.
That's that. Yeah, the flower petals we will explain what the flower petals are all
Right,
about.
because I kind of what I had in the book, it shows the little.
The flower petals are trying to draw these wave functions.
Okay.
So when we do the hydrogen atom, we'll look at the pure modes, stationary modes of the hydrogen. And those are the 1s, 2s, 2p, 3s, 2p, 3d, so forth. You'll understand what those are. We'll write down the wave functions for them. Okay, and so those are pure modes of the electron in the presence of the proton and the guiding.
So the stochastic part, the guiding wave is what's keeping that electron from not going below the ground state.
From going below the ground state. Keeps it from going below the ground state. Yes, ma'am.
How does temperature dependence fit in? Because if you approach absolute zero, it goes, the ground state lowers.
The ground state doesn't go down. This is the ground state. At absolute zero, this is the ground state. It means that the guiding wave structure is present even at absolute zero.
I thought they were able to get particles to approach E equals zero.
This is the limit. There's no way to get below this. You can get arbitrarily close to it. In terms of temperature, you have a mixture of these things for a system that's not in isolation and is bouncing off of other things. We'll explain. I have to go through the next step, which is how we understand superposition. But the superposition is always an energy higher than this. This is the bottom. Can't get below it. Yes, sir.
So the stochastic part, does that explain why you're gonna get, I guess, to go back a bit, you're gonna get at Gaussian on points for where you measure where the electron is, since it's guided by the guiding wave.
So what explains the difference between different members of the ensemble? That each one is experiencing a different random force acting on.
Yes, okay.
Does that make sense? Yeah. You try to prepare everybody the same way, but there's something you can't control. Else we wouldn't need a statistical theory. And the difference is this. Each one is experiencing a different stochastic guiding wave structure, stochastic part of the guiding wave structure. Maybe they're all in the same state, so they all have the same resonating and interfering part. But they have different stochastic part. And so that's what explains why different people see the electron, measure the electron in a different place, because since you prepared it and given it to somebody, the electron is in this one is in this way, this one's in a different way. They're all going to end up in a different place. The interesting thing is, if I say, wait another minute before you take a measurement, we get the same result. So some electrons are moving around, but other ones are moving back into that place. So there's motion going on here in the ensemble, but the net result is you still get the same probability distribution from one time to the next. Right? Does that make sense? This is not changing, but it doesn't mean that the electrons aren't moving. Only statistically, the ensemble is not changing. Yeah. Okay. This is a very important point because it was one of the key things about the hydrogen atom that was a puzzle. The hydrogen spectrum, there seemed to be a lowest state. Why doesn't the electron just fall into the proton? There seemed to be something keeping the electron out from the proton. Same explanation as this. Although for us, we've just posited a box. We haven't explained how we made the box. Okay. With the electron and the proton, in the vicinity of the proton, is the electrostatic attraction between the two that keeps the electron close to the proton. So it cannot lose all of its energy because the stochastic wave is constantly exciting it. So it comes into a kind of steady state. Okay, questions about this so far? Okay, so notice the next state up, n equals 2 state, different probability distribution, different guiding wave structure. So, and so forth, for n equals 3, n equals 4, all with different probability distribution, but stationary. Okay, so they're resonating modes, not just one mode, a whole sequence of modes that you can generate. This guiding wave that will move the electron around and generate these different ensembles. Okay, so remember, we started this with a time-dependent Schrodinger equation. And this, if we have, say, the particle in a box, which is the potential as I wrote it. Okay, when we found a pure mode, we'll solve one pure mode. In fact, the sequence of pure modes will each satisfy this equation. But a superposition will also satisfy this equation. If I take a superposition of these modes, let's suppose psi of x of t is equal to some constant times psi 1 of x plus another constant psi 2 of x. And these are the two lowest states. I could take any pair of them. In fact, I could take a whole bunch of them. I don't have to take just two, but I'm going to show you two, because then you can figure out the rest. So this is a superposition. What does it say about the guiding wave structure? The guiding wave structure is not a simple combination of the two. Somehow, the ensemble has a kind of interference that's going on between these two pieces, and you'll see how this works. I'm going to calculate the probability for this. So these numbers, these are constants, these coefficients, constants, complex, possibly complex. All right, let's expand it out. Star C1 psi 2 star psi 1. All right, 4 terms. The first two are like the probabilities for the stationary states by themselves, right? These are the probabilities we got for the ground state or the first excited state. These do not depend on time. And now we're going to multiply them by some number squared. Okay. So that much looks like we're adding probabilities. But the bottom two terms are interference terms. They show the way in which this thing is not simply a simple adding of probabilities. There's something interesting going on here. Let's take that first one. Okay, so psi 1 was a combination of a spatial part and time dependence. I've taken the complex constant there. And psi 2, the first excited state, it has a different frequency than the ground state. In fact, it's 4 times the frequency of the ground state for the particle in the box. So omega 2 is 4 omega 1. And we're going to take the difference between the two frequencies. They're different, the difference is not 0. So this is going to be e to the minus I 3 omega 1 t 1 star of x psi 2. Well, remember, if we wrote down these spatial parts, okay, so that's That's that term. And we're gonna multiply by C1 star C2. Complex number. And this one is the complex conjugate of that. Right? This is the complex conjugate of this. So psi 2 star, psi 1, going to be d I 3 omega t1 and 2 over L sine pi x over L sine 2 pi x over L. So then we're going to add those together. What do we get when we add them together? Well, we got to be careful. We got these coefficients out here. We have to multiply by the coefficients first. But let's suppose, let's take that C1 equals C2 is equal to 1 over, I have to choose 1 over square root of 2 to make total probability to add up to 1 in this case. Okay. So let's suppose that, and let's see, you'll see that it works out. So then this is 1/2, this is 1/2. So let's do 1/2 of this plus 1/2 of this complex conjugate. So we get then 2 over L. The spatial part is the same for both. What do we get for this complex exponential plus its complex conjugate? Add them together, divide by 2.
Oh, you saying add
Add this one to this one.
divide by 2?
Yeah, divide by 2 because C1 star C2 is 1/2.
You're asking what will that give us?
Yeah.
What that give you, like side 1, side 2, or?
No. This plus this. Add them together, divide by 2. Come on, guys.
Cosine
Cosine of what?
pi or 3 omega 2.
Cosine 3 omega 1t. Good, thank you. So, okay, so the probability has got, the first two terms don't change in time. Remember, the stationary states don't change. So this was like the probability multiplied by some constant. But now we've got two new terms which have a time dependence. The probability is going to be changing in time. So now it matters. I hand everybody out. I prepare 1 million systems, hand them all out. Okay, wait 1 minute, measure your position and report back. Make a probability. Okay, now instead I do it again, but wait 2 minutes. Now I get a different probability. It's not a stationary state anymore because it has more than one frequency. And the difference in the frequencies gives you a time dependence. The probability. So now the thing is moving. The electrons were moving before, but the ensemble wasn't changing. But now even the ensemble is changing. So this is what we're going to study. What's the meaning of this? And can we also, from the wave function, can we determine something, again, statistical, about the motion of the electrons, even in the case of the stationary state? The electrons aren't stationary. Probability is stationary. Electrons are moving. So that's where we're headed, is to extract more information about the state from the wave function. Okay, so your homework problem is going to be, here's the probability. We almost worked out here. Almost everything is here. Okay, you're going to verify that the total probability is 1. If I make this choice, and you're going to find the average of x and average of x squared, and look at the standard deviation. The uncertainty of x is going to depend on time and the way that you're going to work out.
So this is telling us that the ECD ensemble depends on time, is that what you're saying?
Yeah.
So that, what would that, what do you mean when you say?
Okay, let me do it again. I give everybody, I'm going to prepare 1 million copies. Hand them all out. Everybody wait 1 minute. Okay, make your measurement, report back. I get an ensemble distribution. That's odd, is what I get. Do it all over again. Okay, everybody, wait 2 minutes. Measure, report back. Those probability distributions can be different. Right? If they're in stationary states, they're not different. It's the same. But in this superposition of two states, probability is changing in time.
So the superposition, all the pure modes.
Not all pure modes, I just took 2.
Okay, oh, yeah. It's the superposition of two pure modes. This is for a particle in the box.
Yes, particle in a box. Yeah, I put in the particle in a box right here.
Not the ensemble.
But in general, there's going to be a frequency spectrum. So this is the generic result here is the probability distribution, and the superposition of pure modes is not itself stationary. Right? Pure modes are stationary, but a superposition of pure modes is not. And the time dependence depends on the difference in frequency of the pure modes being selected. Okay, so see you on Monday.